set them equal to each other. And simply for comparison, I'm going to get rid of the fractions, and this is going to be tension 1 times mass 2 equals tension 2 times the sum of those two masses. So here's the deal. When I look at this, clearly tension 1 must be larger than tension 2. To make tension 2 equal, it's getting multiplied by a larger number over there. So therefore, tension 1 greater than tension 2. Just by some, just reasoning this out. So here's the deal, though. That was a linear situation. It works pretty much the same way for a situation with some rotation involved as well. So let's look at that. So let's again have a mass on an air track. And there's going to be a pulley over here, though, this time. And we're going to wrap the string around the pulley and be pulled straight down. So there's air track, so there's no friction, and pulley is just attached to some base, right? Now, the pulley has a radius R. The mass has its own mass, M. Let's call this mass of the cart, because typically you have what we call carts on an air track. The pulley itself now has a mass of the pulley. The pulley is going to get affected by the string. So we pull the string down with tension 1. And we kind of have to assume that there's no slipping of the string, and so there's going to be tension 2 here as well. And as the string moves over the pulley will be rotating in this direction. And the cart will be accelerating in that direction. So if this system is accelerating, well, the pulley experiences this angular acceleration in that direction, yes? Awesome. Well, looking at these objects separately, here's our pulley. Now we have tension 1 pulling this way on the pulley, but the string comes off. There's tension 2 this way. But what we know is that there will be an angular acceleration that way. The block dealt with separately just has T2 acting on it, and it will experience a linear acceleration in that direction. Okay, well, there is a link between linear and rotational or angular accelerations, and we're going to take advantage of that. So there's the link between the two. Real easily, what I know from this situation, oh, by the way, yeah, don't forget there's mass of the cart and there's mass of the pulley. In terms of the linear acceleration at the rim of the pulley, that has to be equal to the acceleration of the cart. So if I solve for this, it's quite easy. It's just going to be T2 divided by mass of the cart. Then I can equate this to what's happening angularly on the pulley. And also what I know about this is that the sum of torques about the pulley have to be causing that angular acceleration. And sum of torques is just moment of inertia times angular acceleration. Well, those torques are T1 times radius, which is counterclockwise, right? So there will tend to be this counterclockwise torque that way. And there's also this clockwise torque this way caused by T2. So I can write those in, and T1 times radius, remember here's the radius, radius times torque 1, there's a radius times force, and I'm going to recognize that this is going to be a negative torque, same radius times C2, and there's my sum of torques. Well, it's moment of inertia times angular acceleration. This is a solid disk for this pulley, so the moment of inertia of a solid disk is 1/2 mr squared times angular acceleration. But angular acceleration is equivalent to linear time, divided by radius. So there's my linear divided by radius. That's the same thing as alpha right here. But here's something that's kind of cool. Okay, we're going to start to see this simplify a bit. For example, this radius in the denominator cancels one of those guys. And also, I have an acceleration, but I can make a substitution. This is kind of neat. I can substitute this business in for that acceleration. So rewriting this, I get 1/2. Oh, by the way, I'm sorry, mass. This mass is the pulley's mass right there. 1/2 mass of the pulley multiplied by this business, T2, divided by mass of the cart. And over here I've got the sum of torques, so this is radius times T1 minus radius times T2. Those are the two torques. There's torque 1, torque 2. Okay, further simplification has to happen. I'm basically hoping to make a comparison here between tension 1 and tension 2, just like I did with the linear situation. Not really solving for anything in a numerical final answer kind of way, but I want to be able to make this comparison. So I essentially need to solve for one of these torques, and then that allows me to make this valid comparison. So what I really think I want to do, try to wrap this up here, is I think I want to solve for T2. I don't know why I feel like that'd be easier. Now, how do I get there? Okay, well, what I can see is that I've got, sorry. I missed a radius, didn't I? I didn't cancel both of them. I only canceled one. So there's one left. Sorry about that. Now, that's actually kind of important because I can see that I have radius, radius, and radius. Radius in every term. Cancel, cancel, cancel. And I can rewrite this as, just to clean it up, T1 minus T2 is equal to 1/2. And it's interesting here, I have a ratio of masses. Mass of the pulley divided by mass of the cart times T2. So solving for T2. What I'm going to do is bring this whole term to the other side. Because I can then factor out a T2 from both of those terms. This is going to equal let's see. Okay, so that changed from a negative to a positive, so that changes over here to a negative, but because I flipped it, it's now positive. And factor out my T2. So that's a 1 minus 1/2. And I get the ratio of the masses. And that factored out of this term. Okay. So dividing both sides by this. Okay, I'm going to rewrite that a little cleaner for you, with more room. And I'm going to simplify this a little bit. So I'm just going to say mass of the pulley divided by 2 times mass of the cart. There. So in what we see here, it's going to allow us to reason out a valid comparison. Why do I have a minus sign? I need to have a plus sign. What's going on here? Oh shoot. So okay, way back here when I'm messing around at this line. Sorry about this, guys. I'm going to be basically subtracting this term from both sides. So I will have a minus here, but I have the minus T2. So I'm going to multiply everything by -1. And so that flips this one, makes that one a positive, that a positive term. I subtracted T1 from both sides, so this should be a negative T1, but when I multiply by -1, that becomes a positive T1. So this is a plus. Wow. Apparently not on my A game for math today, but okay, bear with me here. Essentially, if I look at this, this is more or less a ratio of 2 masses. Mass will always have a positive value. So this term, this entire term in the denominator of the fraction, is always going to be greater than 1. As long as we acknowledge that the pulley has mass, then we're adding something to 1 here. That if we discount the pulley's mass, so if we treat this as an ideal pulley with no mass, well, then we're simply dividing by 1. 0 here makes that whole term go away. This divided by 1. However, since this is always greater than 1, we're dividing T1 by something greater than 1 to equal T2. So there's a conclusion we can come to. T2 is less than T1. It must be, if the pulley's mass is taken into account. I'll write that down. If the pulley's mass is ignored, or if we consider just an ideal pulley, then T2 would equal T1. And that's simply because, well, the rotation here is not affecting anything if there's no mass. And that's how we initially looked at these problems, right? If you recall, well, we ignored mass of the pulley. We just said, okay, that's going to equal that, which is going to cause an acceleration. Brilliant. Turns out, though, that, well, the rotating pulley actually matters. Okay, so that's enough for now. This one's gone on long enough. Thanks for watching. I'll catch you next time.